Welcome to the Tech Talk podcast, where we delve into the fascinating world of technology and distributed systems. Today, we're focusing on a critical topic that forms the backbone of much of our modern digital infrastructure: achieving consensus in distributed systems, particularly when faced with Byzantine faults. These are those tricky situations where some nodes in the network might behave incorrectly or even maliciously. So grab your headphones and let's explore the complexities of consensus algorithms, leader elections, and the innovative designs that help us maintain order and reliability in distributed systems. To kick things off, let's clarify what we mean by consensus in the context of distributed systems. Picture a group of friends trying to decide on a restaurant. Everyone needs to agree. But what happens if one friend insists on a place that nobody else likes? In distributed systems, reaching an agreement among nodes, those computers or servers, is crucial, especially when some of those nodes may not be trustworthy. This is where consensus algorithms come into play. There are several notable consensus algorithms, including VSR, Paxos, Raft, and ZAB. These algorithms are specifically designed to handle Byzantine faults effectively, but they have a limitation. They can only tolerate a certain number of faulty nodes, specifically less than 1/3 of the total nodes in the system. This threshold is critical because if too many nodes fail or act maliciously, the system can break down, leading to inconsistencies. At the core of these algorithms is the concept of total order broadcast. You can think of it as a series of rounds where nodes come together repeatedly to reach an agreement. For this process to be effective, consensus algorithms must satisfy several properties: agreement, integrity, validity, and termination. These properties ensure that all nodes eventually agree on the same value, that the value is legitimate, and that the consensus process wraps up in a reasonable time frame. Now let's shift our focus to leader election, which is a vital aspect of consensus systems. To make decisions efficiently, we need a unique leader. However, the process of electing that leader also requires consensus. This might sound a bit paradoxical, but it's essential for maintaining order. Systems manage this using epoch numbers, which help ensure that only one leader is active at any given time. This prevents confusion and keeps the decision-making process streamlined. Another important concept in consensus systems is overlapping quorums. When nodes make decisions, they need to ensure that a sufficient number of them agree and that these agreeing groups overlap. This overlap is crucial for maintaining consistency across the system, especially when nodes may be temporarily unreachable or when network partitions occur. Let's contrast consensus algorithms with something called two-phase commit, or 2PC. While 2PC ensures all participants in a transaction agree before committing, it lacks the fault tolerance that consensus algorithms provide. Consensus algorithms require a majority of nodes to participate, which helps maintain integrity even in the face of failures. However, it's important to note that consensus systems do have limitations. They typically require a stable number of nodes and can be sensitive to network issues, which can lead to performance degradation when things go awry. This brings us to practical implementations of these concepts like Zookeeper. Zookeeper is a distributed system that implements consensus for coordination and configuration purposes. It ensures atomic and linearizable operations even when some nodes fail. What's fascinating about Zookeeper is its design features, such as distributed locks and fencing tokens, which help manage concurrent operations safely. Let's break this down a bit further. In Zookeeper, distributed locks are implemented as leases with expiry times. This means that if a node holds a lock for too long without releasing it, the lease expires, preventing indefinite holding and potential deadlocks. Additionally, Zookeeper uses fencing tokens to avoid conflicts between clients during process pauses. This is managed through a system of monotonically increasing transaction IDs known as ZXID and version numbers. Referred to as C version, these mechanisms ensure that even if a client tries to perform operations out of order, the system can maintain consistency and integrity. As we wrap up our discussion, it's clear that achieving consensus in distributed systems is a complex yet essential challenge. The algorithms and mechanisms we've explored today, like VSR, Paxos, Raft, and Zookeeper, play a pivotal role in ensuring that our digital interactions remain reliable, even in the face of faults and failures. In conclusion, the world of distributed systems is both intricate and fascinating. The challenges of reaching consensus, especially with Byzantine faults, require robust solutions that ensure reliability and consistency. Whether it's through leader elections, overlapping quorums, or innovative designs like Zookeeper, the principles of consensus are foundational to the technology we rely on every day. Thank you for joining us on this journey through the complexities of distributed systems. We hope you found this episode enlightening and that it sparked your curiosity to learn more about the technology that keeps our digital world running smoothly. Until next time, keep exploring and stay curious.